This is a very short lecture to help you make sure you understand the key points of a Maxwell-Boltzmann distribution curve. And these are the curves that, just in real short, typically will have either kinetic energy or velocity or speed, something like that, of particles on the x-axis. And then the y-axis is always the number of molecules or particles. So probably the most important aspect to keep in mind to be able to understand and interpret these graphs is that the y-axis is the number of molecules. So, for instance, this many molecules have a speed equal to this, speed or velocity or kinetic energy, whatever the x-axis is. A larger number of molecules, okay, whatever this value would be, have a speed equal to this. And so where is the most likely speed that molecules that are represented by this curve, what is the most likely velocity? Well, the most likely velocity is the velocity at which there are the most molecules, right? Which is the peak of the curve, okay? So the peak is always the most likely velocity because it has the most number of molecules at that speed, okay? Now, the reason that the x-axis can either be speed and velocity or essentially equivalent. Velocity has a vector direction associated to it, but we don't need to worry about that in here. And we're treating kinetic energy and velocity as the same because each Maxwell-Boltzmann curve represents only one substance, okay? Represents only one substance. So each substance is going to have its own Maxwell-Boltzmann distribution at a specific temperature. So one Maxwell-Boltzmann curve represents one substance that's at one particular temperature. So basically, you're trying to find out what is the predominant or most common speed or kinetic energy of a substance at a particular temperature. We know that kinetic energy is directly proportional to temperature, right? Okay. So if we're only talking about one temperature and one substance, then we also know that kinetic energy is directly related to velocity. So if you're only talking about one substance, the mass is not changing. It's not a variable. So it's okay, kinetic energy and velocity should have a pretty direct relationship. Alrighty, so one other area of confusion. As I said in the last slide, the most probable speed or velocity is at the peak of this curve. Okay, it has the most molecules. What's a little confusing to some people is the average kinetic energy or average speed is a little bit to the right of the peak. And that's, if you look at this curve, it's skewed to the right. See, it's got this tail off to the right. And because of that the average velocity is actually a little bit to the right of the peak. And we're not going to worry about root mean square speed at this point. All right, so any point on the curve can tell you how many molecules have that particular velocity, right? The area under the entire curve, okay, represents the total number of molecules. Why do we care? Because if we take the same substance and change the temperature, what happens to the shape and location of the Maxwell-Boltzmann curve? Well, let's take this as our standard, the room temperature curve. Here's what the Maxwell-Boltzmann distribution looks like. What happens if we heat it up? Well, a couple things happen. The most probable or most likely velocity or speed goes higher. That's what you would expect, right? We know that if you heat something up, if you increase the temperature, that things are going to move faster, right? And so that's what happens here. Now, the shape of the Maxwell-Boltzmann curve also changes. It broadens. So at a higher temperature, oh, here it is. There's a more spread out curve, okay? Which means there are a larger number, there's a broader distribution of possible speeds. But the area under the curve, in other words, the total number of molecules is the same, okay, for each of these curves. Like, we're assuming you're in a closed container and you don't have molecules escaping. So each of these curves represents the same number of molecules. They're just distributed a little bit different. So the distribution at a lower temperature is sharper, but the total number of molecules hasn't changed, okay? That is it. It's just kind of a quick overview.